Okay, so today I'm going to talk about semigroups. And if I can get my thing to work. Okay, so semigroups. So the point is we want to cover the basic things that everyone needs to know if they want to think about semigroups. So first, what is a semigroup? A semigroup is like a group, except we have less conditions. So a semigroup is a set, say S, together with a binary operation on it, and we insist that this operation is associative, together with an associative binary operation, which takes in two elements of S and gives me another element of S. And we often write S, T is short for S star T. This is the output of S and T. The associative condition says that for all S, T, and U in my semigroup, I have that S times T times U is equal to S times T times U. So what can we say about these things? Well, we can say quite a lot about these things, and there are lots of examples of them. In particular, anyone who likes group theory will be familiar with groups, which are semigroups where we have two additional conditions. We have the identity condition. We have an element which fixes every element. We multiply by it. And we have the inverse condition, which says for every element, we can find another element which undoes it when you multiply by it. Okay. There are lots of semigroups which are not groups, and we want to talk about those as well today. I want to sort of assume some knowledge of group theory, though. So there are lots of words which come from which like describe similar classes of algebras. So we have semigroups here. I've mentioned groups already. Semigroups are closely connected to these things called monoids. So monoids are like semigroups, except we have the additional assumption that there is an identity element. So monoid is a semigroup with uh, identity, which we call a 1. So we require that 1 times S equals S times 1 for all S in my semigroup slash monoid, if it's an identity. Groups are stronger than monoids if you accept the standard definition. I have this sort of weird uh, thing going on where I like to count the empty set as a group, which would mean not all groups are monoids. But if you accept the normal definition, then um, groups are monoids. And there's also this class of things called inverse semigroups I want to talk about. Which sound quite similar to groups if you're not familiar with them, because they're like semigroups with inverses, and that's what groups are. But they have inverses in a weaker sense than groups have. So when they say they have inverses, we don't mean the same thing that we mean in group theory. Yeah, we mean a weaker thing. Although the inverses of a group, let me fix that screen share thing. The inverses in a group are inverses in the inverse semigroup sense, but the converse is not true. Okay. And we have these things called inverse monoids to sort of make a square here, inverse monoids, which are inverse semigroups are also monoids. Let's move the word semigroups here to make it more laid out. And then groups are to the right of all of this. Okay, so uh, first there's a definition which I didn't give you, which is for inverse semigroups. The reason I didn't give you an inverse semigroup definition yet is because there's a lot of equivalent definitions of an inverse semigroup, but we want to know what an inverse is in the context of an inverse semigroup in order to define inverse semigroups. And we can do that in a minute, but before we do that, I think I want to give us a better idea of how just normal semigroups work and monoids by extension, because monoids are very similar to semigroups. They just have this identity condition, which it turns out doesn't really do very much. So let's look at semigroups first. So semigroups. So how do we study semigroups, and what semigroups do we have? Well, we can study semigroups in a similar way that we study groups. There are lots of ways of studying groups, but the uh, two I want to focus on now are we can have groups act on things. So we can think of groups as groups of permutations. We can make a group uh, act on a set by assigning each element of the group a permutation of the set. And sometimes we insist our permutations are like continuous or like, you know, automorphisms of some structure or something. And we can also do the other way around, where instead of embedding our group into a larger group of automorphisms of a thing, we can think of our group as a quotient of some other group. So like a free group usually. So we can give a presentation for our group, which is the same as viewing it as a quotient of a free group in a nice way. And we can do both of these things with semigroups with slight modifications. So, uh, so first, I want to talk about the quotient one first. So semigroups as quotients. So every semigroup is a quotient of a free semigroup. So semigroups are what count as what's called a variety of algebras. Semigroups are defined by taking a set and putting some operations on it and insisting the operations obey some laws. And the law for semigroups is the associative law given here. Groups have some other laws, but semigroups only require this law. But the point is, I've got some algebras defined by some laws, and this is enough to conclude that there are free objects in this category of algebras. So, so first we have free semigroups. Free semigroup on a set X. Uh, so here I'm going to think of X as a generating set for my semigroup, and it's just all the strings over X. You may have seen this if you've seen standard way of defining free groups. Free groups are thought of as like strings over a set X and the like formal inverses of the things in X. And semigroups are the same, but we just don't need the inverses because we don't insist we have any. So the free semigroup on the set X is the set, it's often called X to the power of plus. This is all the strings over X, which are non-empty. So this is, let's say W naught, W1 to WK, where here my W letters, WK are in X. Let's move this to the side so there's more space. And K is some natural number, which is not zero. There is no empty word here because I don't insist I have an identity. And this has the operation of concatenation. And this is a binary operation and it is associative. It's not very hard to check that. Okay. And this is indeed free in the sense of free objects. So I can think of X as a subset of X plus, where I think of a word of length 1 as the same as an element of X. So X naturally maps into X plus. And if I have any function from F, from X to some semigroup S, which is a semigroup, then there exists a unique map from the free semigroup on X to S, which makes this diagram commute. This is a function. This is the usual inclusion map, and this is a semigroup homomorphism. This is I didn't tell you what a homomorphism is, but you'll be unsurprised. It's a map from a semigroup to another semigroup, which preserves the multiplication. Okay, so this is it's free in this sense. So the next thing we want to do is say, so in particular, if I have the free semigroup on a set with like one element, this is isomorphic to the positive natural numbers with addition. So e.g., A plus, this is isomorphic as a semigroup. So there's a bijective homomorphism to this semigroup. with plus. And this is not a group because it does not have inverses. However, it does embed in a group. Most semigroups do not embed in groups. We'll get more into that later. Okay, so this is free semigroups. Free monoids are very similar, except we have an identity element. So free monoid on X is often denoted X to the power of star. So star is exactly the same as plus, except now I'm allowed to have empty words as well. I can just copy this definition, put it there, and I can remove the requirement. I guess the way I wrote this thing would be allowed to be 0 because the word of length 1 is like W0 in it. So this is also this, but I now also have this thing, this epsilon, which denotes the empty word. It's an identity. So you'll see here that the free semigroup is obtained from the free monoid is essentially obtained from the free semigroup by just adding this thing here, this identity. And it's actually true in general that if you have any semigroup, you can turn it into a monoid by just adding one element. So here is a observation. If S is any semigroup, then we can obtain from S a monoid S power of 1. This is what it's usually called. It's, it's quite confusing. So the power of 1 often indicates you're not doing anything, but this is the data notation for adding an identity, where S to the 1 is defined to be equal to S. We take a disjoint union with a set with just 1 in it, and we give this a binary operation. And for all A, B, and S1, AB is defined to be equal to AB. If these are both in S, it's A if B is equal to 1, and it's B if A is equal to 1. And these cases are not quite disjoint, but in the case that they're both 1, the last two things agree, so it's not like a contradictory definition. And it's very easy to see this is associative. Yeah, so exercise, check this is associative. We just need to check the cases that some of the A, B, and C in our product are 1 or not. And there's not very many cases. It's pretty clear. Okay. So semigroups and monoids are very closely linked because every monoid is a semigroup, and every semigroup can be turned into a monoid with just one more element by adding 1. Okay. So this gives us an idea of semigroups. So I want to give you some more examples. So far I've only given you one semigroup, which is the free semigroup, and I guess the free monoid. So I guess this is for any set we have a free semigroup and a free monoid. I want to give you more examples because these examples aren't very good examples because these examples actually embed in groups. So these are not giving you anything new if you're familiar with group theory. So some more fun examples. So yeah. So the first one I want to give you is the sort of least groupy example I can think of, and this is called a left zero semigroup. So first, left zero semigroup. So if I have any set S, so if S is a set, we can define the binary operation on S by A star B is just equal to A. This is sort of the left projection map, as it were, from S squared to S. And it's very easy to see that this is associative. So for all A, B, and C in S, A times B times C is equal to A, because that's the left projection. And A times B times C is equal to AB, because that's the left projection, which in turn is equal to A. So these things agree. This is associative. So this makes S a semigroup. And this is as far away from being a group as possible, essentially, because if we have any uh, like groups are what's called cancellative. If I multiply to, if I've got a fixed element of a group and I multiply it by another element of the group, then I can figure out another fixed element of the group. I can figure out what my original element was by multiplying by its inverse. And this is like very false here. So it is not true here that AB equals AC implies B equals C. In fact, this implies nothing at all because this is just always true. If we look at the Cayley table of this, so semigroups also have Cayley tables like groups. So Cayley table for when I take S to be a set with like 3 elements. I have this A, B, C, A, B, C. If I take this element to be the left element, it's always the left element, so that each of these rows is like a constant. This is very unlike groups. So, and in fact, in groups, each row would be a permutation, and this is how Cayley's theorem works. This is how we make groups act on sets. At least one of the ways of making groups act on a set. You can have a group act on itself by you know, taking an element and having it shift the elements of the group by translating them. And here, this doesn't work at all. Although we can translate them, but they're not like bijections at all. In fact, they're not even injections. Okay, so I told you that I can think about semigroups acting on sets like I can with groups, and this is true. But if we see here, the standard thing from Cayley's theorem doesn't quite work because if I look at, say, right multiplication by A here, it does exactly the same thing as right multiplication by B. So if I have this semigroup act on itself on the right by translations, then these columns are the same, which means I'll get A and B defining the same function. So this won't be a faithful action. But we can fix this by turning S into a monoid. So, but with S1, we get this new Cayley table. A, and now the 1 gives me an A again. B, 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 the 1 gives me a B. C, 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 the 1 gives me a C. But now I have A, B, C, 1. And now every column is different. So if I think of each of these things as a translation, they are different. Yeah, which will be important in a second. Okay, so I want to give you, before I talk more about the translation, I want to give you another presentation, which is different from things you might see in groups. So in groups, every monogenic group, what's called a cyclic group, is like a cycle. So if I know the order of a group which is generated by one element, this automatically tells me what the group is. This is not true in semigroups, but it's almost true. So example of a quotient of, say, I take the free semigroup on A. I can define a presentation the same way I would with groups. I can say what the generators are. Here the generators are A, and I can add some relations. So groups, we can simplify our relations by replacing them with relators. We say which things are equal to the identity. In semigroups, we might not have an identity, so we can't do this. But what we can do is we can write a set of rules with equalities between them and say that we insist these relations hold. And this will induce a congruence on our free semigroup. And then we quotient the free semigroup by all the things which are forced by this relation, and we will indeed get a semigroup at the end. So I can add the relation that say A cubed is equal to A to the 5. This gives me a semigroup presentation. So how many elements does the semigroup have? Well, if we thought of this as a group, this rule would be equivalent to saying that if you divide by A cubed on both sides, as it were, I would get that the identity is equal to A squared. So this would be the cyclic group of order 2. However, this is not a cyclic group of order 2 because this is a semigroup presentation. And we do not have inverses. So what do we have here? We have our element A. We don't have an identity at all in this semigroup because there's no reason we would, essentially. We have A. We have A squared. If I multiply this by A, I go to A squared. Here I'm essentially constructing a Cayley graph of the semigroup. And unlike a group Cayley graph, the graph is not symmetric. It's a directed graph, and the direction matters because we can't invert things. And then I can go from A squared to A cubed. And then I can go from A cubed to A to the 4. And then I can go from A4 to A to the 5th, but I already have A to the 5th. A to the 5th is A cubed. So I can go back like this. And these are all A's. So this semigroup actually has 4 elements, and you can check that there is no more consequences of these elements. And this is a 4-element semigroup. We say here A has threshold 2 because it takes 2 A's so it has threshold 3 because it takes 3 powers of A to get to the start of this cycle. And it has period 2 because it takes 2 A's to go through the cycle. So this is, it looks like sort of like a lollipop. And it turns out every monogenic semigroup is like a lollipop like this. And the ones which are groups are precisely ones where this sort of stick has length 0. And if it was a monoid, it would be exactly the same, but I'd have an identity here at the bottom, which connects to the root of the lollipop. Okay. And this doesn't embed in any group, as we can quite clearly see. Cyclic groups are just, the cycle. Okay. So yeah, I want to get back to this. So this, like, I essentially want to prove Cayley's theorem for semigroups. So Cayley's theorem every semigroup can be viewed as what's called a transformation semigroup. Unlike with uh, groups, we can't just have the set we're making transformations on be the semigroup itself, because the semigroup might not be a monoid. But if the semigroup is a monoid, then we can just use the thing itself. And if it's not a monoid, we can just adjoin an identity. So first, what do I mean by transformation semigroup? So if X is a set, we define Tx, the transformation semigroup on X, to be the set of all functions from X to X with composition. As the binary operation, and this is associative. This is well known. Uh, and yeah, so the theorem says that if I have any semigroup, it embeds into one of these semigroups. So, if S is a semigroup, then there is a set X and an injective homomorphism phi from S into the transformations on X. And it turns out we can always take this X to have at most one more element than S. So proof. So first we embed S into S1 with the standard embedding, and then we embed S1 into the transformations on S1 using a map called phi, where phi of S is the map which takes an element of S1, takes T. Here I'm using right actions, notably. This says I take this and I apply it to T on the right. TS. This is a semigroup homomorphism because S T phi of U is equal to UST, and US phi T phi is equal to UST. And the associative law says that these are the same. So this is a semigroup homomorphism. And it's an embedding because also S phi of 1 is always equal to S. So we can always recover S from the function because I have an additive. If I went straight from S, this wouldn't work. Like in the example with this left zero semigroup, it doesn't work because these columns are not the same. So these columns are the same. So I can't recover the element from the column. I can recover the element from the column at the bottom because I've added this one, which makes me able to tell what my element was. Okay. So that's the sort of basic stuff of semigroups and monads. Okay, so how do we go about studying these things? Well, we want to study these things using what's called Green's relations, which essentially tell us how close our semigroup is to being a group. Okay, so how do we define Green's relations? So there's a bunch of them. But before I talk about like how they work, I essentially want to talk about the idea behind how they work. So uh, when I have a semigroup and I want to study it, it's useful to be able to tell how much I can move around in the semigroup without losing information. Because if I have a group, I never lose information by moving around because I can move from any element to any other element by just translating it. But when I have a semigroup, it's possible to have an element when I can't translate back from the elements to a previous element. So, for example, if I look at the this semigroup, I look at the natural numbers, where here I have 0 as a natural number. With multiplication, this is a semigroup, and I know this has 0 in it. So like 0 times uh, 5 is equal to 0, and 0 times 4 is equal to 0. 0 times anything is equal to 0. So once I get to 0 in my semigroup, if I'm doing some calculations and I have a 0 come about, I've instantly lost like all the other information in the semigroup because nothing else in the semigroup has any effect on the 0. I'm sort of stuck in this sub semigroup. And in fact, like this is what we call an ideal of the semigroup. So here 0 is an ideal of n, where here ideal means it's a sub semigroup and it's closed under multiplication by all elements of the semigroup. It's the same idea as in rings, except I don't have like an additional operation here. So this is not required to be like an additive group because I don't have like an additive operation necessarily, although it is in this case. So yes, semigroups have these things called ideals. So we want to track, okay, how much can I go back and forth between things? And Green's relations sort of track this. And it turns out if I'm in the situation that I can go back and forth as much as I want, this is exactly the case that I'm in a group. So here is a claim, it's a theorem. Uh, if S is a semigroup, and for all X in S, the maps rho X and lambda X from S to S defined by rho X of S equals Sx. So this is multiplying on the right. And lambda X of S equals X. Sorry, the XS. So playing on the left are bijections. So this is saying I never have this issue where I sort of fall down into an ideal. I can always move around wherever I want. Then this implies that S is a group. Some people might complain that the empty semigroup has this property. So the empty set with the empty binary operation is a semigroup, and it has this property. I like to think of the empty set as a group because I want this theorem to be true, and there's many other reasons that I think the empty set should be considered a group. If you want to read more about that, see my website where I rant about that a bit. But if you don't like the empty set being a group, then you can just add, S is a non-empty semigroup to this statement, and then it becomes true with the standard definition of group. Okay, so the going around things really is the part of being a group that matters because if you can go around everywhere, you actually are a group. Yeah. Okay. So I don't necessarily want to give the full proof of this. I can do it if you want, but I want to show you how you get the identity out of this because it sort of indicates the idea behind how these arguments work, at least the flavor of the ideas. So like moving around is useful. So how do I get an identity? So part of proof. So I will prove that if S is non-empty, then it has an identity element. So if S in S is fixed, then I know that for all elements of the semigroup, I have a bijection by translation. Then uh, for all T in S, the map, which is multiplying by, let's see, by T on the right, uh, will have, sorry, by S on the left, will have something which maps to S. So I guess I should not have the T. So then like lambda S is a bijection. So lambda S has S in its image. So there is T in S such that lambda S T equals, I could use write actions to be consistent, equals S. And I'm going to claim that this T is going to be the identity. So this means here lambda ST, remember, is ST. So this is going to be the thing that's supposed to be the identity. So I claim that T is an identity. We claim T is an identity. And it's going to work because I can move around whoever I want. So here T fixes this element S on the right, when T is on the right, which means because I can move everything around, I can essentially move this S around to any other part of the semigroup and it will fix that as well. So now if I have another element, U is an S, I'm going to claim that T fixes U as well. Then because multiplying by S on the right is a bijection, there is something I can multiply S on the right by to get U. So there exists, let's say, U prime in S such that U prime S is equal to U, which means thus UT is equal to U prime ST. And then ST is just S because T fixes S. And then I can get rid of the S again. So because I could move from S to U, and I can move back again if I want, I can sort of copy this property of T being a right identity. So T is a right identity for all elements of S. By the same argument, I can find an element T prime, which is a left identity. So meaning it fixes everything and I multiply it to the left. Is T prime in S such that T prime U equals U for all U in S. And this means that T prime is a left identity. And if I look at the product T prime T, T prime T, this is equal to T because T prime is a left identity. It's also equal to T prime because T is a right identity, which means T equals T prime. So this is an identity. So we have an identity because this thing is both a left and right identity. And if I have an identity, I can construct inverses because like everything has a thing which multiplies it to get to the identity. And you can check if a thing is like a left inverse and a right has a left inverse and a right inverse, then they agree. This is a fairly standard group theory check thing, but it's like the same sort of flavor. Okay, so this is how that works. So why did I bring this up? Well, because it sort of gives you an idea of how semigroups work. It tells us we want to be able to move around things, and that's the sort of key thing. But it also relates to green relations. So Green's relations are all about how much we can move things around, and they relate to ideals as well. So I want to define Green's relations now. And Green's relations will also relate to inverse semigroups, which I've been holding back on for a while. Yeah. So Green's relations, there are five of them, and they are always in a lattice like this. So first one are like there are an equivalence. Each Green's relation is an equivalence relation, which can be defined on any semigroup. So if S is a semigroup, we define five equivalence relations on S. My fives and S's look very similar. I'm sorry about this. This is a this one is a five. Uh, okay, as follows. So I have what's called the H relation. I'm not very good at drawing in script things. But this is a script H. I have a script L. I have a script R, which is particularly hard to draw for me. Uh, I have a script D. It's supposed to be a D, and I have a J, which this. Okay, so these are the Green's relations, and these are equivalence relations, and they are ordered thusly. So I have H, I have L, I have R, I have D, and I have J, which is above the entire thing. And these measure how much I can move around in my semigroup. And when people study semigroups they're not familiar with, typically the first thing to do is try and get a handle on how these things work. So I want to explain to you what they are, and I'll tell you how to get a handle on them in what I think is probably the most important example, which is the full transformation monoid. It's the semigroup of all transformations on a set, because every semigroup embeds into one of those. Okay. So what are they? So first definition. So the first ones to define as quite perhaps unintuitively are L and R. So what is L? L tells you how much we can get around by multiplying by stuff on the left. So L says A is related to B. So these are things in my semigroup. If I can move to the same stuff by multiplying by stuff on the left. So here, we write it like this. This is saying S1A is equal to S1B. So what does this mean? This is the principal left ideal generated by A. So this is the product of A with everything in the semigroup on the left, including the adjoined identity, if it's not a monoid. So this set includes A in it in particular, and everything I can get to from A by multiplying by stuff on the left. Similarly, this one has B in it, and everything I can get to B by multiplying by stuff on the left. So this says I can get to the same places from A and B if I multiply by stuff on the left. In particular, it means I can get from A to B, and I can get from B to A by multiplying by stuff on the left. Another way of thinking about it, if you like graph theory, is uh, like this is the relation which says that A and B are in the same strongly connected component of their left Cayley graphs, or a left Cayley graph of S. So this is strongly connected in left Cayley graph. So I can get between them by multiplying by stuff on the left. And in groups, this is always just like the universal relation because I can get anywhere from anywhere. L is for left, unsurprisingly. So you might be able to guess what R is from that. So this is exactly the same, but using principal right ideals, and you can think of it using the right Cayley graph if you want. So R is AB and S squares such that A S1 equals B S1. And again, it's the same as the right Cayley graph. So how do I define the other ones? I need H, D, and J. So H, it sort of captures the idea from over here. So here we were talking about things which we can use to sort of get everywhere on like both sides. And H is like that. So L says I can go on the left, R says I can go on the right, and H says I can do both. So H is the intersection of L and R. It says it's both L and R related. So H is defined to be the intersection of uh, the L relation and the R relation. And it's the intersection of two equivalence relations is an equivalence relation. I didn't mention why these are equivalence relations, but like it's fairly obvious from the Cayley graph thing, right? Also, like I just sort of said, like this is like defining a function from like S to like some sets, and it's like the things which are equivalent under that function. So this is an equivalence relation. Okay, so what about D? D is a bit weird. D is the composite of L and R. So how does that work? So D, L and R are equivalence relations, so they're binary relations. So I can take the composite. So this is A, B, such that there exists a C in S, such that A, uh, C is in L, and C, B is in R. This is the definition. It's not that obvious that this is an equivalence relation, but it's not too hard to check. So here's the sort of slick way of checking it because it's sort of short. I'm going to hand wave a thing in the middle, but it's not a ridiculous hand wave. So what does it mean to be an equivalence relation? Well, it means it's reflexive, symmetric, and transitive. So I need to show that. So what does reflexive mean? Well, reflexive means it contains the like equality relation. So if two things are equal, then they're both L related and R related. So like you can just take C to be the same thing here. So D is reflexive. This is kind of obvious. In fact, this is sort of a I gave like my 330 students a very similar question to this like last semester. This is not like a hard thing to check. So we need to check it's symmetric. So one way of checking it's symmetric is to say we want uh, D inverse to be equal to D. So I want if a pair of things are related by D, then the pair the other way around is related by D. So here this inverse means I swap the pairs in the relation, which is quite an interesting notion of inverse, which will come back again when we talk about inverse semigroups. But this is not a group inverse, you might notice. um, yeah, so I sort of swap the pairs in the thing, and I want this, and I know that this is true of L and R. So how do I check this? Well, uh, I can do this with some algebra shenanigans. So D is equal to L composite R. And in fact, composition of binary relations is associative. If I look at the binary relations on the set, this is actually a semigroup. But let's do some shenanigans. So D inverse is L composed R inverse. It's not too hard to check that the composite of two binary relations inverted does the usual thing with inverses. So it's the same as taking R inverse and composing it with L inverse. You can just check this from the definition of like composition of relations. It's not very hard. Okay, R and L are both equivalence relations, so they're equal to their own inverse because they're symmetric. This is equal to R composed L, and here's the bit where I'm going to sort of cheat. So R is about multiplying on the right, and L is about multiplying on the left. And what does it mean to be associative in a semigroup? Well, it means if I take a thing and I multiply it by something on the right first, and then multiply it by something on the left. It's the same as multiplying it on the left first and then multiplying it on the right. So like associativity is sort of a commutativity condition. It says that right multiplication commutes with left multiplication because it doesn't matter if I do the right half of the bracketing first or the left half of the bracketing first. So because semigroups are associative, this is the same as L composed R. Okay. This is the only part of this argument that actually doesn't work in like a general magma, which is not a semigroup. Okay. Yeah. So yeah, and that's the definition of D. So this is a symmetric thing. And transitive, what does transitive mean? So for transitive, I want D composed D to be contained in D. And how do I check that? Well, I'm going to do the shenanigans again. So I want to check the L composed R, composed L, composed R is a subset of L composed R. Well, composition of binary relations is associative, so I can remove all the brackets and I can compute the L and the R because the same reason I said over here. So this is equal to want this L composed R. So this thing here is L composed R composed L composed R. I compute the L and the R in the middle. This is equal to L composed R composed R. Because L is an equivalence relation and R is an equivalence relation. These are both transitive, and in fact, because they're reflexive, they're like actually equal to their composite with themselves. So this is equal to L composed R, which is just D. So D is an equivalence relation. Okay. Uh, because it's just like it's an important thing because it's like we can get from between two elements by going on one side and then going on the other side. And we can then go on the other side back again and so on. So this is an equivalence relation. And then what is J? J is the big one of them all, which says I can just get between stuff by multiplying on both sides, which sounds very similar to D, but it's not quite the same. So this is, what did I just do? What the fuck? Sorry, technical difficulties. Okay, so I don't yeah, so J, this is saying A is related to B if the principal ideal generated by A, so the stuff I can get from A by multiplying by anything on either side, is equal to the principal ideal generated by B. Okay, so I can get between A and B by just multiplying by stuff on both sides. And in general, these relations are all different. There's a theorem which says that if your semigroup is finite, then D and J are actually the same. And it turns out in most semigroups, even infinite ones that we care about, D and J tend to be the same. But there are examples where they are not the same. Okay. So one thing I want to point out now is H is talking about two things are H related. If I can go between them by multiplying on both the right and the left, so like either of them, so I can get between them by just multiplying by stuff on the left and by just multiplying by stuff on the right. And this is essentially the same thing as this condition I was talking about a few pages ago. This theorem. Here I said bijections. Actually, surjections was enough. I didn't use ejections in this sort of discussion, but uh, this is equivalent. Um, so it turns out H things are very groupy. So in relation to that thing, and I can prove this if you want, but it's essentially the idea that we went through before. So things to know about range relations. To know. Uh, uh, so the idea we want to think of is J uh, is equal to D uh, most of the time. But not all the time. Uh, uh, H classes are group like. Although they're not always groups. Uh, although, like, I can be slightly more precise than this. If an H class is ever a semigroup, it's a group, and every maximal subgroup of a semigroup is equal to one of its H classes. But it has some H classes. Most semigroups have some H classes which are not groups. There are some semigroups which have all their H classes being groups, and these are called Clifford semigroups, which is a slightly broader class of things than just groups. And in groups, all of these things are just the universal relation, so it's like really trivial. Which is why group theorists don't think about these things very much. Okay. So let's talk about this in the example that I care about, which is the full transformation monad, the full transformation semigroup. So example. This is the full transformation semigroup, Tx. And I'll assume X is like, well, I assume it's finite. I mean, I guess it doesn't need to be finite for any of the arguments, so I'll not assume it's finite, but I recommend thinking of this as like a finite example, even though it doesn't have to be. So what do these things look like? So, and also I'm using right actions the whole time, and like it might be confusing for people who like left actions, but like it really it's important to pay attention to which one you're using right now because L and R are very different on this semigroup, but like they're like symmetric. Okay. So what are the Green's relations? Well, first let's look at L and R because all of the relations except J are defined in terms of L and R. So what is the L relation? What is L? Well, the L relation says which functions can I get between by multiplying by functions on the left. So when can I move from, say, F to G and back by multiplying by stuff on the left? Well, it's actually not too hard. So how do I check this? The thing you want to sort of spot is there is a very easy way of seeing it. It's not like that obvious that it's true, but like it's not too hard to check. But the point is the things are L related, they have the same image. So I claim that F is L related to G if and only if the image of F is equal to the image of G. Okay, so if F and G have the same image, then basically I can go from F to G by just taking each thing in X and mapping it to a thing which F maps to what I want G to map it to, and vice versa. So if image F equals image G, then I can define something H which maps, which will let me go between F and G. Then let H in Tx be defined by uh, Hx. I want it to map to something that F's going to map to Xg, which exists because image F equals image G equals, uh, so let's say X subscript G, where X subscript G is in the pre-image of X under the pre-image of XG under F. So this is a non-empty set because there's something which this is in the image of G and there's something which maps to it. So I can just pick this thing in an arbitrary way. I'm using the axiom of choice here for people who are snippety about that. And here, just by definition, if I apply F to this, I'll get XG. So HF is equal to G, and I can go back again. So here, this is saying if they have the same image, then they're L related. If they're L related, they also have the same image. Because note that uh, H, the image of HF is a subset of the image of F. So if I can get, so if HF equals G, then the image of G is contained in the image of F. And if I can go back again, it's the other way around too. So if F is L related to G, then image F equals image G. So I can check if they're L related by just looking at their images. Okay, so what if I want to look at their R related things? So what is the opposite of image? Well, we can think of this in a sort of uh, categorical way. So the image corresponds to picking a subset of X. So what's like the opposite of a substructure? It's like a quotient, right? So dually, and I'm not going to go through the proof of this because I'm running out of time, and I didn't even start talking about inverse semigroups yet. I probably won't have time for this. Um, we F is R related to G if and only if they correspond to the same quotient of X. And what's the quotient of X? It's sort of the kernel of F and G. So kernel here meaning the equivalence relation which relates things if they go have the same image. So if and only if the equivalence relation x, y, and x squared such that x f equals y f is equal to x, y, and x squared such that x g equals y g. So these are the equivalence relations corresponding to f and g. And in the same way that these correspond to the same substructure, these correspond to the same sort of quotient structure of the set in question. Okay, so what about the other ones? So H is just both. So F is H related to G if they have the same image and kernel. So this is called the kernel of this one is the kernel of G. If and only if image F equals image G and kernel F equals kernel G. What if I want to compose things? So D is the composite of L and R. F is D related. Whoops. And none of this used finiteness, by the way. D related to G. If and only if what? Well, if I have two things and I can find a thing in the middle, which so if it's D related to F is D related to G, this is the same as checking if there's another thing H, which is the same image as F and the same kernel as G. And if you think about this for a second, it's quite easy to convince yourself that this is the same as checking that the image of F has the same cardinality as the image of G. So this is the same as image F. Or in other words, the number of kernel classes is the same. And this makes sense even if the cardinals are infinite. There's just no restriction there, really. Uh, yeah, yeah. Okay, so that's D. What about J? What if I can get between F and G by multiplying by stuff on two sides? Well, as I sort of hinted at earlier, it's very common that D equals J, and this is not an exception. Even in this sort of universal semigroup, D is always equal to J. So, and this is the same as F is J related to G. And you can check this if you want. If you have, you can go from F to G by multiplying by stuff. The size of the image can't like go down because if it went down, it wouldn't be able to go back up again. So they have to have the same image size. And if they have the same image size, then they're in fact D related. So they're certainly J related. Uh, yeah. Okay. So that's the Green's relations on the field transformation side. And they are all different except D and J, which is quite common. So this is my Green's relations. Do I have time to do the next thing, which I guess would be inverse semigroups? Uh, so I guess probably not. I think I'll just end it there for today. Uh, yeah. I mean, I guess I want to finish make this recording an hour. So even though this is not part of the talk, I'm just going to keep talking anyway to see what I do in the next 2 minutes. So I want to talk about inverse semigroups. So what is an inverse semigroup? An inverse semigroup is a semigroup in which every element has a unique semigroup inverse, where semigroup inverse is a weaker notion than group inverse. So with semigroup inverse, we think more of like binary relations. Although the full binary relation model is not an inverse semigroup with a usual inverse, it's sort of a special subcase of this. So instead of thinking of in semigroups, we think of functions, and in groups, we think of bijections. In inverse semigroups, we think of partial bijections, and we invert them as partial bijections. And there's sort of an algebraic description of this. So with inverse semigroups, we think partial bijections. So inverse semigroups sort of fall between semigroups and groups. And there's a version of Cayley's theorem for uh, inverse semigroups. It's called the Wagner-Preston representation. It is significantly harder to prove. the group and semigroup versions, and the algebraic definition of inverse semigroups turns out to be weirdly much less useful than the sort of way of thinking of it using partial bijections. So I think certainly when I do work with inverse semigroups, most of the time I think of them as like partial bijection semigroups, and the properties I think of them in terms of partial bijections directly instead of like the definition directly. Um, Although the definition being used directly is also useful sometimes. So I think the main thing you want to do to get comfortable with inverse semigroups is be comfortable with the equivalent definitions and figure out how to basically embed them into partial bijection semigroups so that you can work with them more nicely. Uh, okay, so things to know about partial bijection semigroups, and like a partial bijection is a natural inverse; it's not a group inverse. So what is a semigroup inverse? So semigroup inverses. So every element of an inverse semigroup has what's called a semigroup inverse, and there is a requirement to be an inverse semigroup that this inverse be unique. It is not uh, a consequence of the definition of being an inverse. So there are semigroups which have elements with lots of semigroup inverses, but these are not inverse semigroups. So the definition, so if let's say A and B are in S, then we say A is an inverse for B if we have the following uh, relations. So A is supposed to be equal to A, because like A is sort of canceling out the B here. We also want, and we want B to be equal to B. So group inverses trivially satisfy this because we just cancel the A and the B. But this is a weaker claim. And you can think of partial bijections. Partial bijections satisfy this because this will be the BA will be the identity function on the image of A, and AB will be the identity function on the image of B. So we say a semigroup is an inverse semigroup if every element has a unique such inverse. So definition one, an inverse semigroup is a semigroup in which every element has a unique inverse. So this includes all groups. If you want to see inverses not being unique quickly, if you can think of the left zero semigroup I gave you earlier, you can see that every element is actually inverse for every other element in that semigroup. So this is very not unique in that case, which is why these are not inverse semigroups unless the set has like zero or one element. I'll stop the recording there for today. Bye bye.